feedback from everyone in the audience on which way we want to go as far as where you'd like to touch on another topic, something that's more of interest than something else. Good to see some friendly faces. Good to see some new faces.
The slide deck will be available.
Thank you, Glenn. And for everyone who likes to read ahead, if you will scan this QR code and look, you will find the empty slide deck. It's just a placeholder. So you can either scan the QR code and save the file. One of my personal favorite tricks is if you take a photo of the screen, you can read the QR code later from your photos. And that's the easiest way to send it to someone, text it, email it, whatever. So, and we're still getting set here if you want to. If you're on the corners and want to get up and walk over and take a photo of the QR code, feel free to. Yes, the linked presentation is empty. So when I finish this presentation sometime this afternoon or this evening, I'll copy all of these slides to the empty presentation. That gives me a chance to correct those errors that everyone finds in the presentation before it goes out in circulation. But sharing the QR code for the slides is one of my favorite things. Gives you a more direct path and waiting on the conference and everything sorted up to share it after the fact. So 9:59, I feel like we're closing in, so we'll go ahead and get started. Let's see, about me. Trent, I'm a mentor with 4561. I'm a long-time battery nerd and want to share a little bit about my passion for batteries and wiring. I began using sealed lead-acid batteries in 2003. That with portable X-ray bands. These were a couple of battery packs that we set up compared to the FRC battery banks. Each of these is over 300 pounds, 360 amp hours, 2000 watt inverter, 100 watt charger. Some of the lessons I learned, let me go back. Note the blue, let me go ahead and just gesture. The blue fuse here comes into play in just a second. Note that it's mounted on plywood. That I learned that you need wire for low impedance. I was very much worried about overcharging glass master gel batteries from the alternator. Turns out I ended up needing to use single welding cable to the alternator to get enough charge through the system. Using voltage to estimate remaining battery capacity was a non-starter. Had to track the amp hours. And finally, that fuse plug that I mentioned. Loose connectors smell like smoke. I thought I was near a barbecue restaurant. It turns out that the system was in the early stages of attempting to start fire. It would draw 150 amps for as long as 6 minutes, 7 minutes while the X-ray processor was warming up, so high currents. Quick pass through my technical background. I have a BS in electrical engineering, a master's degree in materials engineering, and I've been a registered patent agent with the USPTO since 2017. My journey in FIRST started 13 years ago with my son in first grade in junior FLL. Mentored First Lego League. No booing, but First Lego League is probably still my favorite. First program. Was a judge advisor, ran an event. Let's see, I'm currently mentoring with the Terabytes 4561. Proud to share that I'm a recent Little Flowers nominee. And I've also volunteered as a CSA at FRC events. Let's see, my approach to FIRST, I feel like first and foremost, we're teaching students how to be members of an effective team, how to collaborate, communicate, get along with your team, help them when they get out in the world. Want to teach engineering best practices, a quest for excellence, and encourage a growth mindset that just because you can't do something now doesn't mean that you can't learn. Nobody starts out knowing how to do everything. Everyone starts from somewhere. This is my favorite quote. I must confess, the first time I ever saw it was on a billboard looking out the hotel room at the convention center. But I absolutely love it. I think it encapsulates a lot of the FIRST ethos about using robots to build kids. We're going to touch on robot power delivery in 3 different sections, starting with characterization, because this part applies to everybody. Everybody has batteries, everybody needs to know. Then we'll touch on improving the battery wiring for lowering the impedance, and then some on pit battery management for event management. Act 1, battery characterization. When you look at the cost of fielding a robot, batteries are actually pretty cheap. 2 batteries for $100. For the cost of a Kraken, you can get enough. For the cost of a Kraken, you can get 2 batteries. So 2 orders, 4 batteries. That's enough to field a robot for most events. Bad batteries, on the other hand, are very expensive. Think what it costs to have your robot die on the field. The team doesn't get to execute on the plan. It doesn't live up to their expectations. So we're going to touch on how to know when it's time to recycle a battery. We're going to touch a few on team quotes, and then talk about urban legends. Raise your hand if you have ever heard your drive team say one of these. Here we go. It's pretty universal. Batteries are very often blamed. Who here has ever seen the drive team come off the field and say, that was an awesome battery? Wow, great, I love it. Respect, teaching, understanding, that is awesome. That we had several power problems with the robot when I started looking at it, working with the team. We had brownouts on the field, stuttering. Someone had labeled batteries with red, yellow, and green. We're not sure who. We're not sure what the evaluation criteria were. We also had batteries labeled bad. There was one battery I found on a bench labeled bad, do not use. Okay, clean the terminals, charge it up, testing. Great battery. We used it in tournaments for 2 years. We renamed it Darwin. And another thing is, this is a mystery. I'm only guessing that students carry the batteries by the cables, judging by the number of loose terminals and broken ring terminals. But every student I asked said they do not carry the batteries by the cables. So it's a mystery. Touching on some urban legends here, and often urban legends are simply actions that continue after the reason for taking those actions no longer exists. Students sometimes think the battery must be just off the charger for it to be good for a match. I mentioned on the bad do not use batteries, that there is some superstition around if the drive team has a bad experience with the battery, whether it be in a match, whether it be in practice, they all chalk it up to the battery and then think that's the issue. It's not the issue. And there was one that was particularly confusing to me because I've never used the old battery chargers that were ferro-resonant chargers. If you left the batteries on those too long, it would cook the batteries. If the charger lost power, the charger became a load on the battery and it would drain the batteries. So when I first joined the team, they were very emphatic about we have to unplug the batteries before we leave the pits. I finally left batteries plugged up to the charger in the lab for a week without draining them before the team would accept that, yes, we do not have to unplug it. Battery charging, it's both simpler than you think and more complex than it seems. That charging a battery normally takes 3 or 4 hours. And it doesn't matter what the battery is, how hard you're charging it. It's a little like having a tall glass and going to a fountain drink dispenser and trying to get a Coke, and you want a full glass, you push it hard, you run it hard, you get lots of foam, and you come back and you didn't get a full glass. So you can either charge them slowly for a long time and get a really full battery, or you can charge them really fast, but you're not going to get a full charge. That at FRC events, your batteries are almost never fully charged after you've used them once that day. Because if you look at the stages of charging here, this is a graph for a 3-stage charger. Often you'll see 2-stage chargers, and if anybody has a programmable power supply with a voltage limit current limit, it's a 2-stage charger. You set your max current, you set your max voltage, and it will follow the discharge curve in the two starting sections, bulk and absorption. Well, what happens is, for most batteries, if you notice the red line, how it tapers down, the charge current tapers off during absorption, most FRC battery chargers, they've got a threshold that once it crosses that line, it turns on the green light that says the battery's charged. That doesn't mean the battery's actually fully charged. What it means is you've gotten 85% of the charge, you've gotten what you're going to get quickly. So it means that your battery is going to be used in competition at less than a full charge. Because if you look, there's quite a bit of charge that still takes place after you leave the float. But one of the things to catch here is it probably turns on the green light while you're still in the absorption phase. And for absorbed class mats, like we use in FRC typically, that's going to be 14.7, 14.8, 14.9 volts, depending on the charger, and it drops the voltage. This voltage, where it disconnects from the absorption, is important because the most common way for teams to evaluate the batteries is using a battery beak. It was a huge leap over just using a multimeter to check battery voltage. But a multimeter and a battery beak will give you excellent estimates for battery state of charge and health as long as you take the battery off of the charger and wait 24 hours. Very seldom done at FRC events. Part of the challenge is when it comes off of absorption, it takes a higher voltage, electronic potential to force current through the battery to cause the charging to happen. That's why you see the charging voltage was 14.7 volts, but when you've taken the battery off the charger, anything really above 12.7 means the battery is fully charged. If it idles at 12.7, what you have is a lot of surface charge, which makes the battery voltage look higher than it is. We'll talk about battery testers in a minute, and one of my favorites, if you plug a battery in that's too fresh off the charger, it tells you to turn on the headlights because it's an automotive battery tester. Let's see, the battery can get a little confusing. There's a lot of information on there. Personally, I think the most valuable piece of information is the internal resistance of the battery. None of these really tell you anything about the battery's ability to deliver power. They do give you a little information about the battery state of charge. Is this a fully charged battery? They don't tell you if it's an awesome battery. Here's the way the battery beak works. It starts by taking let me back up. What we're going to touch on here in the battery beak, if you can see the photo, there's V0, V1, V2. V0 is no low voltage, V1 is 1 amp, I'm sorry, it's not V2 is 18 amp low voltage. So what the battery beak does is it starts with open circuit voltage. This is just, when you plug it up, the voltage that you read, then it applies a 1 amp current and measures what the voltage droop is for the 1 amp. Then it applies an 18 amp current pulse and measures the voltage drop. And it uses those in Ohm's law to estimate the DC impedance of the battery, which is a great place to start. But the most useful information is that battery impedance, but battery impedance is very non-intuitive. Battery impedance does not reflect necessarily state of charge or necessarily battery capacity, but it kind of indicates both. But it's non-linear and it's an inverse relationship. Here is for a single battery between the impedance between 30% and 100% charged. It varies in a nonlinear fashion. Again, it's an inverse relationship. The higher the impedance, the lower the battery capacity, the lower the state of charge. Here it is for fully charged batteries, but batteries of different capacities. Again, it's an inverse nonlinear relationship. So it's non-intuitive. That it is hard to gauge, well, I've got one battery that's at 14 milliohms and another one that's at 17 milliohms. What's the performance difference between those two? What's the impact going to be? So we wanted to find something that was easier to understand, more intuitive, and gives us a better indication of how much power this battery can deliver to a motor. How fast can we make that robot go? Cold cranking amps is where we set it. One standard is the SAJ 537. There are multiple standards for how cold cranking amps are measured. I just picked this one because it's the one most familiar in North America. Cold cranking amps is also a very non-intuitive test. It's kind of backhanded. That it's how many amps that a battery can deliver into a 0-degree motor for 30 seconds without dropping below 7.2 volts. It is not a quality evaluation, it's a pass-fail. That if the battery passed this test, it means the cold cranking amps was actually higher than what they tested at because it passed. If it failed, all you know is that it didn't have that many cold cranking amps, but you don't know how many it was. And these tests are really slow, freeze everything down, hard to do, so that's not what any of the battery testers do. That I've used all three of these automotive battery testers. I actually have all three of those with me. When you get the slides, there's actually links to where you can purchase the two on the left. The top down's my favorite just because it seemed to be the most intuitive for students. Just keep mashing a button and they get all the numbers they need on screen. $50. The middle one there is less than $20. A little more fiddly with the menus. The one on the far right, I bought on eBay. It's no longer available, but it was used in an awesome FRC battery study in 2017. When you have the slides, if you click on it, it's a link to that study. Awesome data. There are lots of battery nerds in the last 10 years in FRC, so there's lots of great data out there. But these use conductance to evaluate and estimate cold cranking amps. So when I looked at it on the scope, there was no useful information I could really show you. It was a small AC square wave imposed on the battery voltage, small loads. But they measure the conductance with AC waveforms, and then they use proprietary techniques to estimate cold cranking amps. So even those aren't shared, but the top battery testers, that's part of their business. So it's a continuing development. The battery beak was awesome and amazing for what it did. It was a huge leap, but I think now there are better testing methods just because that doing this is part of their regular business model. But the automotive cold cranking test is not the be-all, end-all. You need a second component, and that is a battery load tester. The load tester doesn't do, its primary function is measuring how much energy that battery can deliver. And it does it by actually running the battery down and measuring how much power it can deliver. The one on the left is the Mountain Radio battery, computerized battery analyzer. Those are 250. In the middle, you'll see an electronic load bank. You can get those on Amazon anywhere from $60 to $100. The one on the far right, I do not remember the price. I want to say it was on the order of $150, $200. I've used the two on the left. Actually, the one in the middle is my favorite because it can run in standalone mode. So, like when I was at CSA, I tested all the batteries in the CSA lumber cart. So I brought two active loads, and I could have two batteries running and discharging at the same time. So I recommend getting at least one of those. It's worth the time to get one of those and test batteries for at least once a season. We did have a battery once that passed the cold cranking amps test that failed us on the field, and it turns out the actual load test would have caught it. Jump in. We may not get all the way through, but if we get the information you guys want, that's more important than getting through all of my slides.
So I realized the middle one. How would you set the shutoff voltage to be if you're doing that?
Well, that is a great question. What cutoff voltage do you use when you're using the electronic load bank? The other question that should follow that is what test current do you set on the load bank for your testing? And the answer is, it doesn't really matter. I like to use the max current it's got, just so your test time is as short as possible. The most important thing is for your cutoff voltage is that you use the same cutoff voltage when you're testing all of your batteries. I've settled on 10.5 volts that we will see here in just a couple of slides, something that impacts how you select that voltage. Generally, the higher the load current you use, the lower the voltage you want. And that leads us into an interesting question here in just a minute. One of the things that's important is you've got the battery tester, you've got the load tester, you've got the cold cranking amps tester. It's only useful if you collect the data and record it and use it. So we use a battery test log. We always intend to do all the testing back at the lab before the event. That's not how it happens. That here you can see a chart from one of our events where we've labeled how many cold cranking amps we measured, then we start tagging what battery went into what match. That's important because if the drive team says there was a problem, you can go and pull the drive station log. Because if there was a problem, you know you have a good battery. Then it means you either had a problem with wiring, there was a loose connection, a poor connection somewhere, or you had mechanical binding on the robot, and one of your current channels, one of your motors was drawing more current than it should have. So it lets you know, oh, that was match 29, we'll go back and look at the log. If the drive team is convinced it's a battery issue, you pull the battery, you charge it, you run it through the load tester. You verify it is or is not an issue. There are some issues with bad batteries. I did a lot of work at our North Carolina State Champs, helping teams with battery issues. The two biggest things I saw regularly were battery terminals were loose, and I do have to say, I was working with the team, and I said, oh yeah, these battery terminals are loose, you should use a different battery. And a student turned around holding the battery by the cables and handed it over to go in the robot. It doesn't. It's that guy. It's that one guy. That's who does it. So it's like, okay, I see the problem, and I showed the team how to go through all of their batteries, find one with tight terminals. This is the one to use in your next match. That, again, using the battery beak, teams can get distracted into using the charge percentage as an indication of battery quality, but really all it means is how recently that battery came off of the charger. If you have a battery that does test poorly, usually it will test poorly on the cold cranking amps first. That means that your battery terminals are getting loose, they're getting corroded, or the battery's actually deteriorating. I had one battery that was going to send it to recycling. Cut the heat shrink off the battery terminals, and just found out that they were corroded. It's like, well, that's funny. So cleaned the battery terminals off, put everything back on, retested it, and the battery went back into competition for another year and a half. Saved it from recycling. But also, at times when I've taken the heat shrink off, I found out that the ring terminals on the batteries were cracked or completely broken. Nobody knows how it happened. But recabling the battery with new terminals brought the battery back to life. So it was a bad battery. Turns out it was just a broken terminal. Battery terminals are very loose. Always check on, if you can wiggle the battery terminals with 3 fingers, it's too loose. Pull it. Use another battery. Have someone in the pit tighten up the terminals. I like to avoid actually using heat shrink tubing on the battery terminals because it requires some technique to keep from melting the battery when you're using it. I really like something called splicing tape or self-fusing tape. You can wrap it and it seals to itself. You get a nice waterproof connection, no chance of burning. Too many times we've used the heat gun in the pit and it ends up floating up against something else. I've burned my hand, we've melted pins, we've melted other things in the pit. Another issue that is seen way less frequently, though, loose terminals on the circuit breaker. And I think it's way less frequent because you're not wrestling that SB50 on the circuit breaker nearly as much, but it is moving. Yes, a question? Oh, splicing tape. Splicing tape. $6 a roll or something on Amazon. I've got 3 different kinds. It kind of stretches when you take it off the roll and you wrap it and it self-fuses. It's a little hard to get the technique down the first few times, but after that, it's great stuff. Know your batteries. Oh, yes, sir. Another question.
So West Mountain unit has
Yes.
a fairly low maximum amperage.
Yeah, I think ours is 7.5 amps or 10
Low
amps.
as compared to the way we actually use batteries. Do you
Yes.
have an opinion on that? And they have a very expensive device that you can add to up the amperage.
I would spend your money and time elsewhere. That what we're doing is relative comparisons. We're not doing absolute evaluations of battery performance. If you have these 10 batteries in your collection, you just want to know very best battery, very worst battery. This one should be evaluated for recycling and
So you
replacement.
feel it is indicative to how we use the vast, large current draw that we use, that this test is indicative of its health with regard to how we use it?
No. It's indicative of that battery's ability to deliver power, that it is not modeled on how we use it. You really need to use, and I believe the Advantage kit, they have, or is it, there's ability to replay matches at high currents with loads if you want to get to that level of simulation. And the reason it's not indicative of what we do, and that's a great intro for the next slides that are coming up, is because where your robot grounds out depends entirely on your robot. Someone can hand you a battery, and you're not going to be able to tell where it's going to ground out on your robot until it's run on your robot because of your power consumption profiles. If you are, starting 6 Krakens from a dead stop, all at the same instant, you're going to have a ginormous current spike that is going to depend on the quality of the battery wiring as much as the battery on if you're going to see a brownout. But the relative comparison between best battery, worst battery, in helping you manage your batteries, when to retire, what to use for what match, it is valuable for making a comparison with whatever tester you're using, as long as you're using the same tester and the same settings to test all of the batteries. At a CSA event, at a FRC event, and it's a CSA, I can't leave rolling the phone. I want to measure everything. So I tested all of the batteries, and one of the things I found is one of the batteries, the battery being said it's good, 101% charge, 11 milliohms. A new battery would have a capacity in this tenant test of about 12.5 amp hours. This one had a little over 9. So if you tested the battery beak at the CSA station, that's awesome. You want that battery. If your robot has high current demands, you would have had a risk of browning out with this battery. Yes, sir. I'm sorry, I should have put a number across the bottom. These are 8 batteries. And that the size of the column is how much power that battery had. Notice there are 2 empty spots. Those batteries were dead. One had 0.8 volts on the terminals and would not accept the charge. The other one had 1.9 volts on the terminals and would not accept the charge. So don't count on being able to get a great battery from the CSA. Actually, if you know a battery nerd in an event, teams will come and borrow batteries from us or ask us to test their batteries. Advanced battery programming, just want to throw this up for a second. Just because we can do so much programming these days, there are tons of things that you can do. One that I would like to see more teams doing is capture the minimum voltage seen at the drive station during your match. Because the drivers can't watch, the operator, the coach, they cannot watch the display the whole time to see where those voltage dips are hitting. But it's not the average voltage on the display that sets the performance limit for your robot. It's how low is it dipping. That is how close you are getting to a brownout voltage for your radio or for your Rio. Yes, sir. Keep on going.
So I was trying to do some analysis for got one of the logs. I wanted to see some excursions below some voltage, right? So like excursion below 8 volts, how many milliseconds of those are? Is there any software that excels like in my own analysis?
I'd recommend the 11 o'clock session from the Mechanical Advantage on their data kit. That's where I plan to go next. They're also doing it across the hall right now on data collection and replay. Check out Mechanical Advantage and their the Advantage toolkit. They're the state-of-the-art now for logging and reporting data and analysis. I have exported data from the regular drive station logs and put it into Excel. One of the tricks there is you can do piecewise integration and you can measure, you can calculate how much power your robot pulled from that battery just by taking this 20 millisecond window, this was the current, the next millisecond window, add all of those up, and figure out how much power you're using, which is a segue into what we're about to hit. One of the most exciting things that I have not seen teams sharing, but I know they're doing it, is 2 things. One, if you look at the last bullet item, limiting torque to control wheel slippage. So think of it as traction control for robots. That not spinning your wheels when you're in low traction, shoving. All you have to do, all motors have encoders. You read the encoders, you compare them, you reduce the current limits when you see wheel slippage. And just the opposite, that you can increase the current limit when you don't see wheel slippage, so you get maximum acceleration. The others there in the middle, dynamic current limits based on voltage droop. That you want your robot's performance to degrade gracefully. If you do get in a situation where it's unavoidable, there's been mechanical conflict, something is binding, you've used a lot more power during the match than you normally would, you still want to finish the match. You don't want to burn out. You don't want to lose your in-game points or those ranking points. If you are doing dynamic current limiting, you can see, oh wow, we hit our voltage drooped all the way down to 6.6 volts. Let's dial our drive current motor limits back 10% and see if that works. And if you do the programming right, you can make that adaptive. So if it's situational, you find yourself, you were in a pen or you were rubbing past something, It can lower the current limits to keep you from browning out in a temporary situation and then return the robot to full performance once that temporary situation is changed. Wiring for low impedance, Herbart's law, and this brings us to something on what? Yes, sir.
On the last one, what voltage, so if you are plugging in, like, at what voltage are you really concerned, or where should you be kind of concerned? Like,
You should be concerned when your robot browns out. But that is a great question because you should figure out where your robot browns out. You should put a partially discharged battery. You should put a bad battery in it and run it until your robot browns out, because until you know when your robot browns out, no one else will have your exact load profile, your game strategy, your driver techniques. That will be a valuable piece of information because that lets you know where to set your alerts, your danger zones for the drive team, and lets you know how you need to work on managing your robot wiring. One of the interesting things here, Herbart's law, more or less what it means is the more load you put on the battery, the less usable energy you get out of it. Notice I didn't say the lower the battery capacity. The battery capacity is the battery capacity. But normal batteries are normally rated at a 20-hour rate. So our batteries are rated for 18 amp hours at a 20-hour rate. That means if you draw 900 milliamps for 20 hours, you'll get the full 18 amp hours of battery out of it. That's not how robots work. If you look here, if you draw an average current of 54 amps, you only get 6.4 amp hours of energy out of the battery. Well, it's just technical details. You really don't care as long as your robot is full performance for your entire match. But wouldn't it be nice to know how close to the edge you're getting? Doing the test and knowing where your robot browns out is one piece of the puzzle. And next is using you can get these battery analyzers on Amazon for $20 that I like putting them on the battery chargers. We've got one with SB50s on both sides, so we can take it to other teams and check out their battery chargers. Awesome for several reasons. One, when you plug this up, you can see the actual current flowing into the battery. You can see the actual voltage of the battery, so you can see exactly what the battery charger is doing. It is great for doing a fast estimation. You're charging a battery, is it good enough for me to take it off the charger and send it into a match? It tells you. But if you look here, this says 7.8 amp hours. This is how much power it took to recharge that battery. So that lets you know, okay, we use 7.8 amp hours. You can use that and the 2-minute and 30-second match time to back calculate what your average current was. And then you can come back to the data sheet for your battery and then estimate how much battery capacity you actually have at that average load. And I toss average in there a bunch for a reason. Because average current is not what browns out your robot. It's peak current. But it lets you know how close to the line you're playing within your power budget and the battery's energy budget. So can't recommend these enough. They're $20. Yes, Clint.
have you found any of these type of battery meters that will go both directions?
No.
This is very sensitive to source and load.
Yes, if you look on the left, it says source. That goes towards the thing that's generating the current. The load goes on the thing that's drawing the current. So if you put it on a battery, if you're running the battery on the robot, not at an event, it doesn't meet the FRC requirements for game use because it's an extra device, extra junctions inserted between the battery and the circuit breaker. But if you're practice, off-field, non-event, plug the battery in as the source, and then run your match, and you can actually measure how much power you use. But it's also really hard, unless you're in an off-season event, it's really hard to simulate a real match. But when you're taking your match battery out of the robot, taking it to the pit, putting it on the charger, you put the load cell on the battery, and that will tell you how much energy it took to charge your battery. One funny thing I have ran into with these, for some reason, when I plug them up to the battery the first time, the display is like marble. So if it looks funny, you just unplug it, plug it back in. There's something about a brownout circuit or a power-up circuit that's not sequencing the microcontroller correctly. If I find one that does not have that characteristic, I will shout it from the rooftops. Exactly. Turning it off and turning it back on is a thing for a reason. It's a battery analyzer. If you just it used a lot of RC cars, RC planes, quadcopters. That I think this one's rated for 150 amps up to 36 volts or 40 volts. But I bought the 150 amp versions. I bought the 200 amp versions.
If you buy your Anderson connectors from PowerWorks,
Oh yes.
they have them at PowerWorks.
Yes, and I believe they even sell it with the SB50s already attached. So a great investment, just because it lets you do a focused evaluation of how much energy it takes to charge your batteries, how much current is your battery charger actually putting into the battery, so you can check all the channels to see if you have a weak channel on your battery charger. I have also taken chargers out of service because it didn't stop charging, and I found that the battery's setting at 15.1 volts overnight in the pit. It's like, okay, now that is a suspect battery. We'll take that one, we'll take off that charger and pull it out of service until we can evaluate it. Welding cable goes all the way back to my using sealed lead acid battery starting in 2003. It was a key. Batteries are consumable. Always. They have a finite lifetime. Welding cable and low impedance wiring helps you get more performance out of those. But there's several caveats. If you'll notice, the Anderson connector there for the SB50, it comes in a maximum of 6 gauge. If you do some reading on GTL5, you'll find that there are specific 4 gauge batteries, 4 gauge welding cable that you can get to fit in the terminals, but you just cannot cram 2 gauge in. But in another application, I used ring terminals frequently that I needed smaller ring terminals to fit in a specific location, but all of our load cabling was 2 gauge cable because we were hitting peak currents. A normal pass-fail in that test system was, did the current exceed 550 amps? So we got in the habit of using the small ring terminals. The largest ring terminals would fit, which turned out to be, I believe they were 4 gauge. And we would trim the wires down. So when we were having voltage droop issues with the robot, I thought, well, let's use 2 gauge cable and we'll trim it down, and it worked very well. But attention to detail is very important. I have a sad tale to follow with that here shortly, but you'll have to trim it down. I've got a lot of goodies, the things that I have here and that I talk about. When I leave here, I'll go find a table, and anybody who wants to look at any of the testers or components or terminals is welcome to check. But you have to trim the cables back to fit. And one of the most important things is making sure that your trim area is long enough. You want to follow proper crimping procedures and make sure that you're filling the terminal past the area that gets crimped. Here's an illustration. This is an SB50, again, 6 gauge terminal. And we have welding cable in 6 gauge, 4 gauge, and 2 gauge. And you can see how the wire gauge varies there, the wire sizes. Part of the key is use the largest cable that you can where you can, just because, we don't have room in a robot to use 2 gauge cable, so we just use 6. Using 6 is fine. That meets the safety requirements for the currents that we use in the batteries. But if you use larger cable where you can, then that helps you lower the loop impedance. And when I talk about loop impedance, I just mean from the battery to the power distribution hub, the power distribution panel, because that's where your system, every bit of the current for everything on the entire robot flows through those. So that's the place to focus. So just make advances where you can. When it comes to battery terminals, that we have been using PIM nuts and putting PIM nuts on the actual battery terminals themselves. That gets us 2 things. One, we only use 1 Nordlock washer compared to what Zebracorns shared in their original awesome paper in 2017. Read everything that Zebracorns have shared. It's insane how much effort they put into supporting and educating the community. At the end of the slides, which you will get later, there are links to the Zebracorn papers. The Zebracorn 2.0 talks about the grasshopper nuts there in the center with the aluminum folded piece. That has been the new hotness for 2 years or so. On the left, you'll see the 2 Nord locks with the bolt and washer. Yeah, they've got a nylon lock nut on that. That is discouraged because the lock nut, if it's not fully tightened, it's not loose because it's locked by the lock nut. So you can't tell, does that have 5 inch-pounds of torque on it, or does it have 70 inch-pounds of torque on it? Where if you use a non-locking nut, when it gets loose, it gets loose. There'll be references for all of these on there. The ultimate goal is to make the connection as robust as possible at maintaining the thrust lock to keep it closed.
Do you have any other mechanical lock hardware for batteries? I know there's some like oval lock nuts and some other stuff too.
From everything I've read, there'll be some references. I'll need to add a reference. There is a great bolting guide on what causes bolts to loosen and vibrate. The Nord-Lock seems to be the state of the art if you're not using nut wiring, where you cross drill and wire the nuts in place. Yes, sir.
When you're considering what screws and nuts to use, do you ever worry about the current flow to screw it up, or is that just purely contact and just purely mechanical?
It's just mechanical. There should be 0 current flowing through your nut and bolts. If you look here at this, that there's nothing between the battery terminal and the SB50 terminal. Same thing here. This is the battery terminal on the battery, and this is going to the terminal going to the SB50. Same with the terabyte terminals. There is nothing between the battery terminal and ring terminal, nothing between the battery terminal and the ring terminal. You don't want steel getting into your current flow path. Yes, sir.
What size bolt are you using on that?
It depends on your battery. These are both M5 bolts. The gray MK batteries can only use M5 bolts. That's the largest size recommended for those. If you have the black batteries, the Duracells, those can use M6. It's not as big a difference as you might think, because part of how the Nord-Lock washers work is they count on bolt stretch. So if you're using a 6mm bolt, it requires more torque to get the effective locking function of the Nord-Lock washer. It also comes into play about choosing stainless steel over steel. If you use stainless steel, it has a lower tensile strength, so it takes less torque to stretch the bolt to get that clamping retention for the Nord-Lock washer. If you're using steel, it requires more torque. And what you want to do is make sure you stay within the torque limits of the battery terminal itself, which is a hard number to get from battery manufacturers. It's usually somewhere on the data sheet if you dig for it, but that sets ultimately you don't want to torque the battery more. The terminal's more than that because you risk damaging the internals of the terminal. Yes, sir. The Belleville springs are nice, and I would use them with the terabyte terminals, but there's no good place to put it. What I like about the Belleville springs is that they add height to the stack, and they deflect while maintaining the pressure. So you can visually tell you're losing compression in the spring without losing your thrust force. So they're a great application, but there's not a good spot to use them with the Nord-Locks. So I suspect you could use those in lieu of Nord-Locks because it still gets you to, the other problem I've had is finding them in M6 and M5. If you can find them in M6 or M5, I think they're the holy grail. And what they do is they have a cupped surface, and as you tighten them, they compress, but they maintain that force while they compress. So you can actually see losing the compression before you actually use the application force. Yes, sir?
I just want to note that the Grasshopper nuts are open source. You can download the CAD file, cut them on a them, you can figure out the finish and press them.
Oh, yes. And that's how we ended up getting here, is trying to think of, well, how can we do something like the Grasshopper nuts without needing a CNC? And there's a whole story thing, Cheryl and Chief Delphi about that. We're down to the last couple of minutes. Here's the first robot that we fielded in an off-season event. You can see we've got the 2-gauge on the welding cables, the 2-gauge welding cables on the SB50, 2-gauge for the breakers back down to the PDH. And now we're getting somewhere. That robot died on the field. I could not have been more excited. Why was I excited? This was our first Swerve robot. at, I believe this is Rumble in the Roads, 2 years ago, 2.5 years ago. It was a double robot pen with a less experienced driver, and he tried to power out of it. When he went to power out of it, he tripped the circuit breaker. Radio never browned out, Rio never browned out. Low impedance wiring. Now it was up to programming and the drive team to manage the current limit on that circuit breaker. We had exceeded all the other limits. The limit was no longer what the battery can do. It was no longer limited what the wiring can do. Wrong direction.
Really quickly before you move on, do you know
Yes.
what the torque values are for the gray batteries, the Duracell batteries, or no?
I don't recall offhand. The only thing that jumps to mind is from the Grasshopper Nuts build thread. I think they were saying 70 inch-pounds, which I've been shooting for 6 newton-meters-ish. You can develop some intuition for that, and that's also still in progress because I feel like that there's some techniques that you can do to reduce the lack of compression you will get during use. Here at District Champs last year, we had a robot that died in a match. It's like, okay, we jumped in, we checked the SB50 terminals, those are good, the crimps are good, replaced the circuit breaker, grabbed an awesome battery, had tight terminals, sent it into the next match, and the robot died in the field again. 1 minute and 7 seconds left in the match, and the robot never moved again. There was an impact right here, right, not there, there. That it never moved again after that impact. But it's like we replaced everything but the PDH. But I'm a skeptic that before it died on the field, I'd already asked the pit crew to get a replacement PDH ready. And another mentor asked me, how can a PDH fail? It's like, I have no idea, but that's the only thing we didn't replace. And it turns out that's how a PDH can fail. Attention to detail that was self-induced, that I was not at the meeting when they were wiring up the 2-gauge welding cable, and they twisted the welding cable until the outer strands came off enough to shorten the diameter so they could shove it into the terminal. The ironic thing is if the strip length were longer, it would have worked. It would have been fine. But it just barely grabbed it in, so it had a high impedance connection. So high current, it got hot. More high current, it got hot. But this lasted all the way through District Champs and the 2 previous regionals. But it was an easy problem. All we had to do was replace the PDH before our next match and move every wire that provides power to everything on the entire robot. Our sophomore female controls lead and a female senior jumped in and moved every wire for everything before the match. I did have a mental failure moment here. Raise your hand if you see the failure. Failure for best practices. Okay, we see a few hands. I did not think to tell them that you should remove rings and bracelets before you work in electrical circuits. The robot is completely depowered, but it is the best practice because low voltage, less than 50 volts, is finger safe. You can touch it. But if you have on more rings, they can really lower the impedance to your body, so it's a bad thing. If you short something high current, they can melt your finger. Pit battery management, we did not get through this. Let this thing flow through. Use your pit log. Here you can see we've labeled batteries. We don't have, the match schedule is not out, so we don't have match numbers to put on the batteries, but we taped the batteries when they came off the charger. So if you see a battery with yellow tape on it, it is ready to go in the robot. It will either have the cold cranking amps or the match number on it. Always bench test with the match battery. At Champs last year, I wasn't in the pit. They bench tested and swapped the battery for the match battery after the bench test. In the process of moving the arm and replacing the battery, we pulled the CAN cable for the shooter. So we went in our last match at Worlds last year without a shooter because we didn't do the bench test with the match battery. Other tips for air reduction, I've handed some of these out. I've got some with me if you want to see them. Battery carrying handles for keeping you from wanting to carry the batteries by the cables, safer to carry, and replacement for zip ties, an SB50 clip that stays on the robot. You don't have to keep up with it, you can't lose it. You can tell from 50 feet away, did you put the clip between the SB50 terminals? Let's see, there's lots of FRC battery resources. Controls wiring is hard because the lights come on, the LEDs come on. You can have a really, really, really bad connection with really, really bad wire stripping and really, really bad crimps. The LEDs will still come on. We used a thermal wire stripper this year, 100 bucks a pitch key. We've loved it. Everything went great. Not a single field stoppage, not a single brown out, not a single reboot on the field. Top time saving tip, build a dedicated toolkit just for your robot that lives on your robot cart. Someone doesn't have to race back to the pit, doesn't have to worry about not having the right tool. They've got all the right Allen wrenches, they've got the screwdrivers, they've got everything that they need to do quick repairs. And sometimes you learn by doing crazy things. This is a FRC robot battery baking in the oven at 170 degrees upside down for 6 hours. The method to my madness was this battery was underperforming. I suspected the acid stratification had reduced battery capacity, so I wanted to reduce the viscosity. Sulfuric acid is more dense than water, so it's upside down to encourage the denser sulfuric acid to flow down, and it's heated to reduce the viscosity of the sulfuric acid. And in the end, it did get a 31% boost in battery capacity. Still not match worthy, but I thought it was a great data point. You'd have to ask her, but I'm pretty sure she's at best neutral. But thank you for your time. Happy to answer your questions. Hit me up